Today we're going to talk about two more convergence tests, and typically they're ones that are easy to apply. And so first is the ratio test, and we're going to consider the series A sub n, and we want to figure out whether it converges or not. And in order to do that, we're going to look at this ratio of consecutive terms and take the limit, and we'll call that limit rho. And so the test says that if rho ends up being less than 1, then the series converges absolutely. If rho is greater than 1, then the series diverges. And if rho is equal to 1, or the limit doesn't exist for some reason, then the test is inconclusive, and that means that you need to try something else. And so really the intuition behind the ratio test is to compare a series to a geometric series. And the reason for that is if we know that rho is the limit of the ratios, then essentially what we're saying is that rho is approximately equal to a n plus 1 over a n for large n. Okay, and so if we know that this equality is approximately true, then that's the same as saying that roughly speaking, a n plus 1 is approximately equal to rho times a sub n. And if we were to use this equality over and over again, then we could see that what it's saying is the next term in our sequence is always approximately rho times the previous term. And so in other words, in our sequence, to get between terms, you just keep on multiplying by this constant rho, which you might remember is how we defined a geometric series to begin with. And so this is saying that if we can find the limit rho, then essentially we've shown that our series is approximately geometric, and as long as rho is less than 1, then we know it converges. So the usage for the ratio test, it's great whenever we have factorials involved, and we'll see some examples where that's the case. It's good whenever we have exponentials in our series, and it's bad whenever things are ratios of polynomials. And so by ratios of polynomials, I mean things like k over k squared plus 9. And so that sort of series, the series of k over k squared plus 9, we already know how to deal with that using either the direct comparison test or the limit comparison test. And so it's not the case that we can't deal with these things, it's just that if you tried to use the ratio test on this, it would end up being inconclusive. Okay, so let's see a couple examples where the ratio test does work well. So here we have the sum of n factorial over 2n factorial. And I am going to use the ratio test because it involves factorials, so that's a good idea for this one. And so I'm going to take the limit as n goes to infinity of the n plus first term divided by the nth term. And so to figure out the n plus first term, I need to replace all of the n's in this expression with n factorial, n plus 1's, sorry. And so in the denominator, things are a little bit weird because you need to replace the n with an n plus 1 inside parentheses. And it's easy to forget to do that, but that's really important to put this n plus 1 in parentheses because the 2 needs to be multiplied by this 1. And that's just an easy thing to mess up. And then I'm going to divide by the nth term, which is the same as multiplying by the reciprocal of the nth term. All right, and so now I just want to rearrange the terms so that they're easier to deal with and easier to cancel. And so typically what that means is I'm actually going to want to rewrite things so that the like terms are on the same fraction. And what I mean by that is I had this n plus 1 factorial and this n factorial that really came from the n in the numerator from my original series. And so I want to write them together as one fraction. And so I have n plus 1 factorial over n factorial. And then I also have the 2n factorial term over the 2n plus 2 factorial term. And now I need to figure out a way to simplify these. And the key idea is going to be for factorials to remember that they're just the product of everything that goes below them. And so, in other words, what I'm saying is that n plus 1 factorial, that should be n plus 1 times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. And so I can really rewrite this as n plus 1 times n factorial. And the reason I'm going to stop there is because now the n factorial cancels with the 1 in the denominator here. I can do the same thing for the 2n plus 2 factorial, where that's really 2n plus 2 times 2n plus 1 times 2n factorial. And again, now this 2n factorial will cancel with the 1 in the numerator. And so if I sort of clean this up now and write what I have left over, then I can see that I have an n plus 1 in the numerator, and then I have a 2n plus 2 times a 2n plus 1 in the denominator. And so if I simplify this, you could see that the leading term in the denominator is really an n squared. And so overall, the denominator is much bigger than the numerator. And so this limit has to be equal to 0. And that's by comparing leading terms. And so now this is the value of rho in the ratio test. And so in this case, we can see that 0 is less than 1. And so that means the series converges by the ratio test. And so I want to go back and look at the original series for a second here and consider what that means. And so here we had an n factorial in the numerator and a 2n factorial in the denominator. And your intuition might have been to say, well, 2 factorials, they're probably roughly the same. And so overall, the terms might be tending towards 1, and it might diverge for that reason. But we can see that actually a 2n factorial is way bigger than an n factorial. And what we've shown from the ratio test is, in fact, 2n factorial is so much bigger than n factorial that it does still converge. All right, let's look at this other example here. And so this one would be potentially a good candidate for the ratio test because it has that 2 to the n in the denominator. And so there is an exponential, and the ratio test is pretty good with dealing with exponentials. And so it is the case that this is really an alternating series that decreases down to 0. And so we could just use the alternating series test to conclude that it's going to converge right off the bat. But I just want to get some practice using the ratio test as well. And so here, I'm going to take again the limit as n goes to infinity of the ratio of consecutive terms. I'm really taking the absolute values of these ratios, and so for that reason, I can drop the minus 1 to the n right away. And then I'm going to get n plus 1 to the 5th over 2 to the n plus 1, and then times the reciprocal of the original term. And so that's 2 to the n over n to the 5th. And again, I'm going to rewrite this just so that like terms are next to each other. And so this is really an n plus 1 to the 5th over n to the 5th times a 2 to the n over 2 to the n plus 1. And now I need to do some simplifying of this limit. And the first thing to notice is that the leading terms here match between the numerator and the denominator. And that's because if you expanded out the n plus 1 to the 5th in the numerator, then you'd have to FOIL it out and you get a whole bunch of terms, but the first term would still be an n to the 5th. And so the others don't really matter. And then for the other term right here, the 2 to the n over 2 to the n plus 1, that simplifies because the 2 to the n's will cancel. And so that just simplifies to 1/2. And so if we take the limit of this, then we just get 1 times 1/2, or in other words, 1/2 overall. And that is less than 1, and so this converges, as we predicted before, by the ratio test. And so if we go back again and look at the original series and see what it was saying here, we already know that the ratio test is comparing things to geometric series, and we could see that this is saying that roughly this series is geometric with rho being equal to 1/2. And so in other words, it said the stuff in the numerator doesn't really matter. It still overall behaves like a geometric series.